neural nets or multivariate techniques to search for primary vertices.
Hello, Michel. Hope you can hear me.
I can hear you well, yes.
Now I have to find the correct thing to share. And I have to give Zoom access to it. Sorry for the delay.
No worries.
So you should see the slides now.
Yes, indeed, I see the slides.
Perfect. So sorry again for the delay, and I will now present an update to a deep learning approach to PV finding. Our motivation is the LHCb experiment in run-free, but however, this approach can also be applied to other tracking challenges. But sticking to LHCb, in run-free, we are currently removing all tracking detectors, and we are upgrading the PID detectors. Also, as you have heard before, the hardware triggers will be removed and the luminosity will be increased. So I think it's fair to say that there will be a new experiment at point 8 in run-free. We want to further build on the success of offline quality reconstruction and go further in the direction of real-time analysis. And the challenges have been presented to you already by Louis. And if you see this talk remote, you can also stop and also listen to the GPU talk that will follow by Thomas. Our approach here will be PV finding using machine learning, and we hope there to improve the fidelity and run at high rates. So I'm going to introduce this PV finding algorithm. The challenge in run-free at LHCb will be that the number of visible PVs will increase about a 5-fold. And we learned in the past that the efficiency is mainly driven by the cluster search. And exactly there is where we want to use machine learning. The PV finding project itself is standalone, and it uses toy MC particle generation, toy tracking. And then it does a histogramming or a kernel generation. It then feeds this histogram into convolutional neural networks, which are trained by true PV finding histograms, which have at the PVs a very sharp spike. These are used for training and validation. And as a reminder, the plots have been shown already last year by Henry, and you also see a link to the proceedings. So the first step after the tracking, where we can actually use the production tracking if we deploy this in the LHCb HLT, is the kernel generation. And the kernel generation reduces the sparse three-dimensional data that we have from the vertex locator, which has about 41 million pixels, to a very feature-rich one-dimensional data. So the goal is to find kernel maxima and X and Y in each of the 4,000 bins in this histogram and assign this as a Z kernel value. So you can see in the plot on the right that we have the hits, and then we have sort of Gaussian tubes around these hits, and then where these tracks cluster, there we have a spike in the kernel. So currently this kernel maximum search is done by a coarse manual search and then followed by a Minui minimization step. The kernel is also parameterized, as you can see in the slide, which is a product of these Gaussian PDFs evaluated at their IP X and Y uncertainties. And in the standalone algorithm, the width of this kernel Gaussians is an heuristic width, which is an estimate of how the tracking covariance metrics might look like. And this is heuristic in the proto tracking. So an example of such an output histogram of this kernel density estimator is shown here, where you generally can say that very sharp peaks in this histogram correspond to primary or secondary vertices. And the challenges are here then to find, to really pin down which are real primary vertices and which might be fake. So the vertices might be offset from the peak, they might overlap, or there could be some smaller peaks, which are actually vertices and others are not. Then the following step is feeding these kernel density estimators into the convolutional neural network that is implemented by PyTorch. And we have seen now further improvement is possible by changing the architecture of this convolutional neural network. So the network shown here is a snapshot of the one that we had in 2019. One thing to also mention about this network is that we have a cost function that is modified with an asymmetry parameter. So the cost function would usually be something like a cross entropy, but this cross entropy treats false positive over false negative events symmetrically. And if we introduce this asymmetry parameter, this gives us a handle to balance off the efficiency over the false positive rate. A result is shown here. So you see, as a function of the number of tracks in LHCb, we can reach very good efficiencies, and this is very close to what Florian has shown before for the baseline tracking. So the proof of principle was already established last year, and the improvements that came over the years that we have modified the target histograms, and also we have changed the architecture of the network by also adding X and Y position information. And you can see that for a fixed efficiency of, say, 94%, the false positive rate is about 2 times smaller. And then a next step that we had to take, or that we wanted to take, is to deploy this PV finding algorithm into the LHCb software stack. So currently the algorithm, or before the algorithm, was a standalone thing that was written in Python, but now we need the C++ or CUDA versions to adapt also to the LHCb environment. And so and the kernel generation and also the CNN inference engine had to be deployed in the HLT, and we chose to deploy it in the CPU version of the HLT first. And it runs on the output of the production velo tracking algorithm. And since there are several inference engine evaluators on the market, such as ONNX, but since we have trained this in PyTorch, we decided for TorchScript as the C++ inference engine. Currently, we are collecting and evaluating results with this implementation. And the first results that we obtained look very promising. Another update is concerning the kernel density generation. And since we now used the output of the production velo tracking, we can also use the measured covariance metrics. So we can get uncertainty estimates for the input parameters, for the impact parameters, instead of using this heuristic impact parameter uncertainties. So you can see in the plot below, which has a semi-log scale, that the new kernel density values in red look much more pronounced around the PV regions compared to the old ones in blue. And we hope to get new results with this soon. So to conclude, a hybrid deep learning vertexing approach has been introduced to PV finding. its proof of principle is established, and it has now been deployed in the LHCb software stack. The performance was also further improved, and we are looking ahead to reach further milestones, which would first be to benchmark the performance with the standard LHCb simulation software and compare it to the baseline PV finding algorithm that Florian has presented earlier. We want to retrain the algorithm using full LHCb simulation and also the new kernel densities. Further on, we want to develop an algorithm to assign tracks to primary vertices that were found probabilistically. And currently we are seeing that the kernel density generation is too slow. So we want to develop a fast machine learning algorithm for the KDE generation itself, and then try to combine the algorithm for KDE generation with the algorithm for the cluster search. If we then see that these are too slow, we have still the possibility to prune these machine learning algorithms by weight reduction, or by weight reduction techniques that are on the market currently. So the algorithm, the PV finding algorithm, is in open source code with a standalone package, including toy generation. And you can find the link here if you want to try it out. And it's runnable with a Conda environment. Thanks for your attention.
Thank you, Marian. Are there questions to PV finding? Anyone? I know you say this is some benchmark for the future, but do you have any intuition where this performs better than a classical approach? I don't know. I mean, PV is with very few tracks, or PV is far away from the middle of the interaction. I mean, the 0-0 point. Or...
You also have problems with PVs with very few tracks. So we do see some efficiency there. I can go back. So the standard cut that we use in LHCb for the number of tracks that can be associated to PV is 5, and you see that there's an efficiency turn on in this red region here. But other than that, I think we are in a situation where this is comparable to the baseline. We have to see whether this is better or worse, because we have our own generation currently running, and these numbers that you see here have to be taken with a bit of a grain of salt. But we now have the machinery ready to compare this with the official simulation, so we will have numbers for this soon.
Okay. Any more questions to Marian? That does not seem to be the case. Then thank you again.
Thanks.
And we conclude this session by a talk by Thomas about